Alright, so let's look at example 1. Finding the open intervals where each function is increasing or decreasing. So for the first one, f of x equals x cubed minus 6x squared plus 1. So the first thing we need to do is we need to find the domain of this function. So remember, we're always going to start with the domain because a value can't be a critical number or a relative extrema if it's not in our domain. So for this one, so the domain of this function, so look at the type of the function that it is. F of x equals x cubed minus 6x squared plus 1 is a polynomial. So that means in this case our domain is negative infinity to infinity. Step 2, find our critical numbers. So remember, to find the critical numbers, what do we have to do? That's right, we set the derivative equal to 0 and find values where the derivative is undefined. So in this case, so the derivative of the function f prime of x is equal to 3x squared minus 12x. And so let's go ahead and rewrite this, simplify it so that it's going to be easier to find where it's 0 or undefined. So factor out of 3x, that makes it 3x times x minus 4. And so f prime of x undefined, where is it undefined? That's right, it's never undefined, so we don't get any critical points that way. So then the second part, set f prime of x equal to 0. So that means we're setting 3x times x minus 4 equal to 0. So 3x equals 0 means x equals 0. X minus 4 equals 0 means x equals 4. So our only two critical numbers in this case are x equals 0, x equals 4. Alright, step 3, we have to test these critical numbers to determine the behavior on either side of it. So to figure out where the function's increasing and decreasing. So to do that, basically what we want to do is think of this along the lines of how you found the domain for a radical function that had a higher degree polynomial under it. So something that wasn't linear under the polynomial. You had to pick a test point based on the critical number. So in this case, so basically what we do is we use our domain as a starting point. So remember, our domain in this case was negative infinity to infinity. And we're going to divide that domain up at our critical numbers. So if we do that, so if this is my domain, negative infinity to infinity, well, I'm going to split it up at 0, x equaling 0, and x equaling 4. So my domain then, I'm now going to have intervals going from negative infinity to 0, 0 to 4, and 4 to infinity, based on our critical points. So what I want to do is I want to pick, based on those points, a test point in each of those intervals. So if I know I have somewhere between negative infinity and 0, some number that's there, pick nice easy numbers, because remember, you're usually not going to have your calculator for this. So something like negative 1 is a nice easy number on that interval. That's going to be a test point in that interval. Between 0 and 4, well, a good easy number would be 1. So when you're picking these test points, they have to be inside. Actually, I'm going to pick 2, just for fun. But these test points have to be inside the interval. So, and they can't be the critical values themselves. And then between 4 and infinity, let's pick 5. The number that you pick doesn't matter. What matters is that it's in the interval. So you could pick any number you want as long as it's in each of the intervals. So you could pick negative 1,000 if you wanted to, between negative infinity and 0. It doesn't matter because it can only change signs at the critical points. So the first derivative can only change signs about the point. It can only change its behavior at its critical numbers. So in this case, we're going to test negative 1, 2, and 5. And we're just plugging them into the first derivative to find out what the sign is. So f prime of x, remember, is 3x times x minus 4. So if we find f prime of negative 1, well, that's 3 times negative 1 times negative 1 minus 4. So, and really, we don't care about what the number is. We care about the sign. Is it positive or is it negative? So if we take it piece by piece, so 3 times negative 1 is going to be, so 3 itself is positive. So we have a positive number times negative 1 is a negative number times negative 1 minus 4 is still going to be negative, right? And so if we look, we have positive times a negative, right? Which means then positive times a negative is going to be negative times another negative is going to make that positive. So this is going to be greater than 0. So what's that mean? That means then, so what's that imply? That's implying that f is increasing. Similarly, so for our next test point on the interval 0 to 4, we picked 2. So f prime of 2, well, that's 3 times 2 times 2 minus 4. So 3 is still positive. 2 is positive. So we have a positive times a positive times 2 minus 4. So that's going to be a negative number. So positive times positive is positive. So, and then a positive number times a negative number is going to be a negative number, so less than 0. So that tells us what? F is decreasing. And then our last interval, 4 to infinity, we picked 5 as our test point. So f prime of 5, so that's 3 times 5 minus 4. So 3 is still positive. 5 is positive. 5 minus 4, positive 1, so that's positive. So positive times positive times positive means our first derivative is going to be greater than 0 on that interval, which then tells us f is increasing. So we put all this together. Now we just state the open intervals where f is increasing or decreasing. And if there are none, you, of course, want to state that. But in this case, we do. So in this case, we know that f of x is increasing on the open intervals negative infinity to 0, union 4 to infinity. And we got that from testing our test points on each of these intervals. And then f is decreasing on 0 to 4. All right, so let's look at the second one. So f of x equals x over x minus 1. And we're still doing the same thing. So we're trying to find the intervals where the open intervals where the function f is increasing and decreasing. So same idea. First thing we need to do is find the domain of this function. So our domain is going to be negative infinity to 1, union 1 to infinity. So remember that comes from setting the denominator equal to 0, right? So we have to keep that domain in mind whenever we're finding our critical numbers. So then use the quotient rule, find the derivative. I'm not going to work that out. I expect you to go back and work through how to find the derivative using the quotient rule. But f prime of x in this case is 1 over x minus 1 squared. So find out all the values where f prime is undefined and f prime equals 0 for any critical numbers. So f prime is undefined whenever the denominator x minus 1 squared equals 0. And so that's just x minus 1 equals 0 gives us x equals 1. But can that be a critical number? Nope, it can't be a critical number because it's not in the domain. So make sure you write out why that's not a critical number. F prime equals 0. To find that for a rational function, really what this ends up being is whenever 1 equals 0. In this case, because that's our numerator. So remember, to get there, you would set the entire derivative equal to 0, multiply by x minus 1 squared, which then just gives you 1 equals 0, which makes no sense, right? So in this case, we have no critical numbers. Again, you should state this. But, so does that mean we can't find intervals of increasing, decreasing? No, that just means we don't have any extra points to divide our domain up at. So now we just divide our domain based on our domain. So now in this case, if we draw a number line out, the only intervals we have to worry about when we build our table to test our point values are our domain. So we have negative infinity to 1 and 1 to infinity. So the only intervals you have to worry about are those two. So we have negative infinity to 1 and then 1 to infinity, because that's our domain. We didn't have any critical values to split it up. So next thing we want to do, pick a test point in each interval. So if we look at the interval from negative infinity to 1, well, let's pick a nice easy number. So 0's in that interval. I typically recommend 0's, 1's if you can, because it's going to be easier. And then 1 to infinity, well, we can't choose 0, we can't choose 1, so let's choose 2. Another nice, easy number. So then from here, we want to find the value of f prime of x. So remember, f prime of x in this case, 1 over x minus 1 squared. So in this case, so f prime of 0, that's 1 over 0 minus 1 squared. So numerator is going to be positive. The denominator is going to be positive because we're squaring it. So it doesn't matter if it's positive or negative inside there. If you square something, it's going to be positive. So positive divided by positive, greater than 0. So then that tells us that the original function f is increasing on that part. And then, so testing 2, so f prime of 2. So that's 1 over 2 minus 1 squared. But that's still a positive divided by a positive, so greater than 0, so f is increasing. So then our conclusion, so f is increasing on its entire domain, so f is increasing on negative infinity to 1, union 1 to infinity, and decreasing nowhere. Again, even if it doesn't have anywhere that it is, you still got to tell me that.